Welcome to the lesson 22 of industrial instrumentation. Actually, in this lesson and subsequent lesson, you will find that we will discuss some of the basic signal conditioning circuits. As you know, the signal conditioning circuits are very much necessary in various phases of the sensors, because we need whenever the signals are electrical, we need to process. We have to process that type of signals, and we need some signal conditioning circuits. So, in this lesson and the next lesson, we will discuss some of the signal conditioning circuits commonly used in instrumentations. This is lesson 22. Now, this is signal conditioning circuits 1. Contents of these lessons: positive and negative feedback topology we will discuss. We will discuss the active filters, we will single amplifier structure. At the end of this lesson, the viewer will know single amplifier based active filter, the design equations, advantages and disadvantages of single op amp based active filters. So, basically we will discuss the active filters in because as you know, active filters, amplifiers, sample and hold circuit, these are most commonly used analog signal conditioning circuits. So, we must go into now. Initially, in these particular lessons, we will see that the single amplifier based active filters. In the subsequent lesson, we will find that we will discuss some other more complex filters, even though those need single amplifier, the second order structure, but it has some advantages. So, people go for the multiple amplifier structure or multiple amplifier topology, right. Now, filter type, the filters are frequency selective networks, and they are categorized as low pass, band pass, high pass, band reject and low pass notch, right, and high pass notch. So, these are the typical class of filters we will get. Now, also we have a we can say the delay equalizers or all pass filters, that is also a class of filters that will be discussed later on. So, you see the all pass filters, because in all pass filters will not consider the frequency functions. We basically there will discuss about the or consider the delay of the networks, right. So, that is the reason it is called all pass. It is not part of with the gain, but in the time domain how its delay occurs, that we will see. Now, a general biquadratic filter function is expressed by T s equal to capital K s square plus omega z by q z s plus omega z square s square plus omega p by q p s plus omega p square, where this is a generalized second order structure. So, let us first look at second order structure, because if we have a second order structures, we have a, suppose I have a low pass filters of a second order structure. So, I can have a characteristics like this. Suppose if I take this page, so low pass characteristics will look like this. So, the slope of this will be if this is the frequency omega and this is gain. So, you will find that this will be minus 40 dB per decade, right. Now, the legends are in these particular expressions. You see the omega z is 0 frequency, or q z is 0 selectivity, omega p is the pole frequency, q p is the pole selectivity, and capital K is the gain constant of the circuit, right. So, it is like these are the filter parameters. Suppose if you have a resistance, you know that resistance, if you say just resistance value, it does not define, it does not have any meaning. Suppose you have to define everything, that means the resistance value, its tolerances, its wattage, everything is to be defined, right. So, in that sense only you will get the actual filter. So, similarly, in the case of filter also, you know that you will have some parameters which is to be given, only that in that case your filter will be characterized, right. That is called filter specifications. You see the general biquadratic filter function can also be written as, in last equations we have seen that it is written in terms of pole frequency and pole selectivity, right, and pole frequency, pole selectivity, zero frequency, zero selectivity. Now, in this case we are writing with some coefficients where T s equal to k m s square plus C s plus d upon s square plus a s plus b, where m, c, d, a, b are these are all coefficients, right. So, in this case please note that all this filter function is a complex conjugate poles, right, and complex conjugate zeros if the zeros are there. So, poles are always, you see this denominator functions will define the poles. So, this is always complex conjugate poles, right. Now, k is a gain constant. Now, this all m, c, d, a, b all will be realized by some resistors and capacitors, is not it. A second order low pass filter function is given by the following transfer functions: d equal to s square plus a s plus b, right. Now, in this case that our pole 0 pattern will look like this. Suppose sigma g omega plane, this is sigma, this is g omega, okay. We have a complex conjugate poles and no zeros, right. So, this is called the pole 0 pattern of low pass filter, clear. A second order high pass filter function is given by this T s equal to m s squared s upon s square plus a s plus b. So, you can see that in this case if I make m and c 0, then I can get the, because if you look at the generalized functions that it c, you see if I make m and c 0, I will get coefficients m and c 0, I will get a low pass function. If I make c and d 0, then I will get a high pass function, is not it. You see this high pass function. Now, k is absorbed in m because we have a gain constant k, here also k is absorbed in d. So, we have this is a high pass function. Now, the pole 0 pattern will look like, take a white page, it will look like sigma g omega plane. So, it has a complex conjugate poles and two zeros at the origin, right, double zeros at the origin, fine. So, this is our high pass function, second order high pass filter function. Always you please note that is m, a, d, everything is to be realized by some resistance and capacitance, right, and op amp obviously will be there. A second order band pass filter function is given by the following transfer function, which is given by C s upon s square plus a s plus b, right. Now, in this case the pole 0 pattern will look like sigma j omega plane, right. So, we have a complex conjugate poles and 1 zeros at the origin, clear. This is the pole 0 pattern of a second order band pass filter, clear. A second order band reject filter functions will be given by the following equations: s square plus d upon s square plus a s plus b, right. In this case that d must be equal to, that means the pole 0 pattern will look like, in the case if d is equal to b, then we call it band reject function. The pole 0 pattern will look like, if I take a blank page, so it will look like sigma j omega plane, right. So, we have a complex conjugate poles, these poles always lie on a semicircle and two zeros, complex conjugate zeros will be there, right. So, this is our band reject functions, clear. Now, if it is b equal to d, it is called the band reject functions. If b less than d, it is called the low pass notch function, okay. And if b greater than d, we call the high pass notch function, right. So, in this case what will happen, you know that you will have, suppose I have a second order all pass filter or Diehl equalizers is given by k equal to T s equal to k s square minus a s plus b upon s square plus a s plus b. In this case, these pole zeros are the mirror image of each other. These poles and zeros will be mirror image of each other. You see, this will be k equal to s square minus a s plus b upon s square plus a s plus b, right. It is a mirror image of each other. Now, single amplifier structure, let us look at single amplifier structure, how the because single amplifier structure is the basic structure. We can have a double amplifier structures or also 3 amplifier, 4 amplifier structure, but single amplifier is a it is the cheapest one. So, let us explore that what is the advantage, disadvantage of this type of circuits. Now, single amplifier structure or single amplifier topology can be connected in 2 different way. One is that you put the RC network in the negative feedback path, then we will call it a negative feedback topology. If we put the RC networks in the positive feedback path, we will call it positive feedback topology, right. We will discuss both. Let us discuss one by one. Single amplifier filters can be classified into 3 major categories: positive feedback topology, negative feedback topology. We have also a enhanced negative feedback topology, right. We will discuss that. It is a negative feedback topology with certain amount of positive feedback, that also we will discuss, right. So, it is called the enhanced negative feedback topology, right. Now, positive feedback topology, you see what will happen in the case of positive feedback topology. We will have, in this case, this RC network is placed in the positive feedback path of the op amp, and however, a negative feedback is also given to keep the filter stable, right. Because if you look at the circuit, you see that this is a positive feedback topology, RC networks in the positive feedback path, but if I keep this circuit as it is, circuit will not be stable. We need to make the circuit stable, we have to give some negative feedback. Okay. So, these negative feedbacks are given by these 2 resistance R1 and R2, clear. The transfer function of the network can be expressed in terms of the feed forward and feedback transfer functions of the positive passive RC network. Feed forward transfer function TFFS equal to V3S upon V1S, making V2S equal to 0, right. So, feedback transfer function TFBS equal to V3S upon V2S when V1S equal to 0. From the circuit, we can write that V3S equal to V plus S, that means the positive input of the op amp, equal to TFFS feed forward transfer function multiplied by input V in S plus feedback transfer function TFBS into V0S. And so, solving this, we can write that also we can write that V minus S equal to R1 V0S upon R1 plus R2 upon V naught by S upon K, because small k equal to 1 plus R1. Please note that small k and capital K are different. The small k is the amount of negative feedback you will give in the positive feedback circuit will be determined, whereas capital K is the gain constants of the circuits, right. These 2 are different. Now, where k equal to 1 plus R2 by R1 and V naught S equal to A, obviously output voltage will be equal to the amplifier gain multiplied by the difference of the signals which is coming in the inverting, non-inverting and inverting signal input. So, which can be written as k TFFS 1 minus k TFBS plus k by A, right, small k by A. For an ideal op amp, obviously I can assume that A is infinite, then I can write k equal to TFS 1 upon 1 minus small k TFBS, right. Now, TFFS is equal to, we can write NFFS, that means numerators of the NFFS and DFFS, and feedback transfer function TFBS can be written as NFBS upon DFBS, right. Now, this we will find that these 2 are same, that means DFFS, that means denominator of the feedback transfer function DFBS and denominator of the feed forward transfer function DFFS are same. Why? Let us look at NFFS and NFBS are zeros of the RC network observed from the different ports. Denominator DFFS and DFBS are obtained from the nodal determinants of the RC networks, and thus we can write DS equal to DFFS equal to DFBS. Then I can, these equations can be simplified as TS equal to small k NFFS upon DS minus k NFBS, right. So, salient features of this positive feedback topology, you see what is the salient features. Zeros of the transfer functions are the zeros of the feed forward RC network, which can be complex, right. Quite obvious, you see what I am talking about. Okay, zeros of the transfer function depends on the zeros of the feed forward transfer function, right, that can be complex, clear. Whereas the poles of the transfer functions are determined by the poles of the RC network, the zeros of the feedback transfer function and the factor k. What is this? Let us look at. You see the poles of these transfer functions depends on the zeros of the feedback transfer functions and the function k, okay, ratio, that means R2 and R1 and ds. What is ds? ds is the poles of the feedback or feed forward transfer function, depends on all these three factors, right. Now, negative feedback topology, if you look at the negative feedback, this RC network is in the negative feedback path of the op amp and hence the name negative feedback topology, clear. As before, the transfer functions of the network can be expressed in terms of the feed forward and feedback transfer function of the passive network, right. Now, this is a negative feedback topology. You see, this is a stable circuit, I do not need any positive feedback, whereas in the positive feedback, I mean circuits we have seen that if it is positive feedback, I have to give certain amount of negative feedback, right. Now, we can write here also as before V3s equal to V minus s, which is 0 obviously, TFFs, no, it is not 0 because it is a negative feedback topology. Let us look at, so it is not 0, V plus is 0, right. So, V3s equal to V minus s equal to TFFs into V in s plus TFBs into V0s. So, V0s equal to A, V, I mean this is the output voltage obviously equal to the gain of the op amp multiplied by the difference of the two inputs which is coming, right. V plus s, and since V plus s is 0, in the case since it is connected to ground, so it is coming minus A V s. So, I can write transfer function T s equal to V 0 s minus upon V in s minus T f f s upon T f b s plus 1 by A. As for ideal op amp, A tends to infinity, then transfer function T s equal to T f f s into T f b s. As before we know D f f equal to D f b equal to D. So, obviously, as before we can write that N f f s upon D s, N f b s, T f b s equal to N f b s by D s. So, D s will cancel out. So, T s equal to minus N f f s upon N f b s, right. That means, the poles of the transfer functions will be determined by the poles of the feedback networks or feedback transfer function, zeros of the transfer functions determined by the zeros of the feed forward transfer function, right. So, these are silent features. The zeros of the feedback network determines the poles of the transfer function, the zeros of the feed forward network determines the zeros of the transfer function, right. Zeros of the feed forward feedback network determines the poles of the transfer function, zeros of the feed forward network determines the zeros of the transfer function, right. The poles and zeros can be complex, however, for a stable network the poles should remain on the left hand side of the S plane. That is from basic control theory, you know this to be satisfied. The poles of the RC network do not contribute to the transfer function, okay, because D is getting cancelled out. So, the poles of the RC network whether it is feedback or feed forward transfer function is not coming into the picture. If you assume obviously the op amp is ideal, so I can say that it does not contribute. So, let us look at the enhanced negative feedback topology. We have seen that in the enhanced negative feedback topology, circuit is slightly different. There we have the RC networks in the negative feedback path, but we are giving some positive feedback also in the circuit. This is similar to the negative feedback topology, with the only difference that there also exists a positive feedback. You see here, see negative feedback topology, RC networks in the negative feedback topology, and positive is coming. So, we are giving certain amount of positive feedback, right. We will see that we will get some tremendous advantage by this circuit. So, circuit analysis we get that V 0 by small k s equal to V in S into T F F S plus V 0 S plus T F B S, or V 0 S upon V in S minus T F F S upon T F B S minus 1 by k, or V 0 S upon V in S equal to k N F F S minus upon D minus k N F B S as before. So, design equations let us look at. Among positive feedback signal amplifier filter topologies, we will discuss this, we are not discussing this in details, we will discuss actually when we will consider the circuits. We will find that in the enhanced negative feedback topology, we will get some tremendous advantages which we will not get in the positive, neither positive feedback topology or simple negative feedback topology, right. Now, let us come to the practical circuits which we will realize based on single amplifiers, that means a practical second order filter circuit which is built around a op amp, right. Design equations. Among the positive feedback topology single amplifier filter topologies, the silent key filter is a very popular. For the silent key filters, we generally have the widely used choices which are as follows. We have three choices: equal or equal C design, unity gain amplifier design. In equal or equal C design, you will find all the resistance and capacitance will have same values. Unity gain amplifier design, you will find that the amplifier's gain is unity, so the bandwidth of the circuits will be higher. And surrogate design, you will find that in equal or equal C design, you will find that the sensitivities are extremely high, even though the element spread is very less, all the resistance are of equal value, all the capacitance are of same value, but the sensitivity is very high. In the unity gain amplifier design, you will find that the element spread, especially if it is in low Q, that means QP is less, the element spread we can, element spread is high, obviously is extremely high in the case unity amplifier design, but you will find the sensitivity, some of the sensitivities are identically 0, right. That is a tremendous advantage of the, and this circuit unity gain amplifier design is very popular when I am using the circuits at the low pole selectivity region, because if the pole selectivity is less, obviously we will find that the element spread will be less, right. But if the elements, if the pole selectivity is high, the element spread will be extremely high, though the sensitivities in both the cases will be very low, right. In some cases it is 0. Surrogate design has both is the name of the scientist who has developed this one. He said that if you can make a particular choice of the elements, you will find that the neither it is a very large element spread nor the sense. So, it is a good compromise between the sensitivity and the element spread, right. Let us look at one by one. Equal or equal C design. In this type of all the resistors and capacitors are made of equal value. In major drawback is that the passive sensitivities are very high. Unity gain amplifier designs, in this case the gain of the amplifier is chosen as 1. As you know, the unity gain buffer, concept of unity gain buffer, its bandwidth will be higher, right. And it is found that in this case the sensitivities are quite low and some of the sensitivities are even 0. The main disadvantage of this is that the capacitor spread of this type of design is very high, and it can be, however, if the QP is less or low, then we can use, in that case the capacitor spread will not be that high. And surrogate designs, we have k is always, a small k is always designated, it is assigned value of 4 by 3. In doing so, a good compromise between the sensitivity and the element spread can be achieved, right. So, we can have a good compromise between the two. So, this is silent key, famous silent key low pass filters use a single amplifier structures where we need 4 resistors. Okay, these 2 resistors values are different, this small R1, R2, this will determine the negative feedback which you are giving in a positive feedback circuit. This is your RC network, so it is a positive feedback topology because RC networks in the positive feedback path. Now, transfer function from the circuits I can write V naught S by V in S equal to small k upon R1, R2, C1, C2 upon S square plus S 1 upon R1 C1 plus 1 upon R2 C2 plus 1 upon 1 minus k upon R2 C2 plus 1 upon R1 R2 C1 C2, where this frequency or pole frequency will be given by omega p equal to root over 1 upon R1 R2 C1 C2 and QP equal to root over 1 upon R1 R2 C1 C2 1 upon R1 C1 plus 1 upon R2 C1 plus 1 minus k by R2 C2. and gain constant capital K equal to small k upon R1 R2 C1 C2, right. Now, equivalent equality design is basically actually you will find that in this equivalent equality design for the silent key low pass filter C1 C2 equal to 1 or R1 R2 equal to R equal to 1 upon omega p. So, obviously, k small k equal to 3 upon 1 by q p. Now, unity gain amplifier design is that design equations are C2 equal to C and C1 equal to 4 q p squared C. Now, see the q p is slightly, if it is 1 the capacitor spread is not that much, but the q p if it is 10. So, it is not very uncommon, in that case capacitor spread will be extremely high. R1 equal to R2 equal to R and CR equal to 1 upon 2 omega p q p. For simplicity we take C2 equal to 1, C1 equal to 4 q p square, R1 R2 equal to 1 upon 2 omega p by q p, and surrogate design you see here. The design equations are C2 equal to 1, C1 equal to root 3 q p and R1 equal to 1 upon q p omega p, R2 equal to 1 upon root 3 omega p. So, small k equal to always 4 by 3 upon 1 plus R2 by R1, right. So, it is fixed. Now, this is a high pass filters, you can see we have interchange resistance and capacitances, right. So, if you change the resistance and capacitance, I will get a high pass filter. And you see this is a very handy circuits. I mean, if I have a high pass filters, I mean, if I know the design equations, I can make my own filter. It does not cost much, it costs more than 5-6 rupees. Only op-amp is costly, this resistance capacitance can be ordinary, right. But we need certain amount of tuning. You will find that whatever the prescribed center frequency, pole frequency we have asked for that, we may not achieve that particular frequency. We need little tuning, because these are sensitivity of this type of structure is quite high. Now, from the circuits we can write this high pass transfer function equal to V naught. You see the small k into s square, V naught s V naught by V in s, k s square upon s square plus s 1 upon R 2 C 2 plus 1 upon R 2 C 1 plus 1 minus k R 1 C 1 plus 1 upon R 1 R 2 C 1 C 2. So, omega p equal to root over 1 upon R 1 R 2 C 1 C 2, q p equal to root over 1 upon R 1 R 2 C 1 C 2 upon 1 upon R 2 C 2 plus 1 upon R 2 C 1 plus 1 minus k R 1 C 1. So, it is small k equal to this capital K, obviously k equal to 1 plus R 2 by R 1 in this case, right. And okay, yes, capital K equal to small k equal to 1 plus R 2 by R 1. Equivalent, here also we have equivalent equality design. The design equations are C1 equal to C2 equal to 1, R1 equal to R2 equal to 1 by 1 upon omega p, k small k equal to 3 by 1 upon q p. Same as the low pass unity amplifier design also we have done for the low pass, where k equal to 1, that means unity gain amplifier design. So, obviously, k will be equal to 1 and C1 equal to C2 equal to C and R1 equal to R and R2 equal to 4 q p square into R. CR equal to 1 upon 2 omega p q p. For simplicity, we take C1 equal to C2 equal to 1 and R1 equal to R equal to 1 upon 2 omega p q p. So, R2 equal to 2 omega p 2 q p by omega p. Surrogate design for the high, I mean these structures or high pass structure, C1 equal to q p, C2 equal to root 3. So, it is R1 equal to 1 upon root 3 omega p q p and R2 equal to 1 upon omega p. Small k equal to R1 plus R2 by R1 equal to 4 by 3. So, this is you see this band pass filters. In the band pass case, we need one more resistors R3, all other resistors are same as before we have, but the structure is slightly different, right. It is negative positive feedbacks. To make the circuit stable, I have to give certain amount of negative feedback, right. So, this is our band pass case. Let us see the transfer function Ks as it happens 1 0 at the origin upon R1 C1 whole upon S square plus S 1 upon R1 C1 plus 1 upon R3 C2 plus 1 upon R3 C1 plus 1 minus K upon R2 C1 plus R1 plus R2 upon R1 R2 C1 C2, right. So, as before we can find this pole frequency, pole selectivity and the gain from the expressions, which looks like omega p equal to R1 under the square root R1 plus R2 upon R1 R2 C1 C2, QP equal to under the square root R1 R2 R1 plus R2 upon R1 R2 C1 C2 under the square root whole upon 1 upon R1 C1 plus 1 upon R3 C2 plus 1 upon R3 C1 plus 1 upon 1 minus k by R2 C1, and capital K equal to small k upon R1 C1. Equivalent equal design C1 equal to C2 equal to 1 and R1 R2 equal to R3 equal to root 2 by QP in the case of band pass, small k equal to 4 by root 2 QP, right. Now, unity gain amplifier design, when small k equal to 1, the design equations are C1 equal to C2 equal to C, R1 equal to R3 equal to 9 QP square minus 1 into R, and R2 equal to R, and CR is a constant 3 QP upon 9 QP square minus 1 into omega p, right. Now, for simplicity we can take C1 equal to C2 equal to 1, R2 equal to 3 QP. Now, you see these are all actually we are getting in normalized values, because 1 farad nobody will use. I may use 0.01 microfarad. Accordingly, I have to scale down, I have to scale up the value of R2, so that the time constants will remain same. There is a very simplified way of using. I will have 1, so I can take this 0.01 microfarad. That means I am multiplying it by 10 to the power minus 8. In the same time, I have to multiply this at 10 to the power plus 8, right. So, I have to scale down, scale up resistance, scale down capacitance. So, the total time constants will remain same. R1 equal to R3 equal to 3 QP by omega p. Now, negative feedback circuits, you see that these type of circuits have multiple feedback. So far, we have discussed only about the positive feedback circuit. That means, a single amplifier or second order filter structure, we have discussed the band pass, high pass, low pass. So, that means all these 3 different structure filter functions, the circuits which will realize these filter functions, and based on a single amplifier structure. But in all the cases RC network is in the positive feedback path. So, we are calling it positive feedback topology. Now, let us look at negative feedback topology, even though we have discussed the negative feedback topology, but actual circuits we have not discussed. So, this we will discuss now. They may have 2 types of structures, one is without positive feedback and another is with positive feedback, right. There are 2 types of structures are there with positive feedback. Now, band pass circuit with negative feedback without positive feedback, it looks like this. B input R1, C1, C2, R2. You see this type of circuits also called the multiple feedback circuits. If you look at, there are multiple feedback, there is multiple feedback path. Okay, one is this path and there is this through this path it is coming, right. So, this is called multiple feedback circuits, and there is no positive feedback. The positive feedback is also not necessary to make the circuit stable. Okay. But we have seen that in the positive feedback, if you give certain amount of positive feedback, some advantage we will get, right. That we will discuss after some time. Now, from the circuits we can write that you see minus S upon R1 C2 upon S square plus S upon 1 upon R2 C1 plus 1 upon R2 C2 plus 1 upon R1 R2 C1 C2. We have omega p equal to 1 upon root over R1 R2 C1 C2, QP equal to under the square root 1 upon R1 R2 C1 C2 and whole upon 1 upon R2 C1 plus 1 upon R2 C2, right, and gain constant k equal to 1 by R1 C2. That is quite obvious because there is no positive feedback. So, it is a negative feedback topology, that means RC networks in the negative feedback path. So, this is the filter. These are called the filter parameters, as you know that this is called the filter parameters. Like at the beginning, as I said, if I buy a resistance, you have to tell its value, right. If I say value, that does not make any sense. You have to tell the tolerances, you have to tell the wattage. Once you define all these things, more or less a resistance is defined. More precisely, you have to tell that what type of resistors are these are, whether these are the wire room resistors or this is a carbon film resistors or any other type of resistors. Similarly, here also in the filters also these are called filter parameters. That means these 5 parameters, that means pole selectivity, pole frequency, zero selectivity, zero frequency and the gain constants are they called the filter parameters. Once you define this thing, these 5 parameters, the filters are defined, right. Now, design equations here in the case of negative feedback topology, simple negative feedback topology or negative feedback without positive feedback circuits looks like this. Let us take C1 equal to C2 equal to 1 and R2 equal to 2 QP by omega p and R1 equal to 1 upon 2 omega p QP. So, this is our positive without positive. So, this is a circuit is with positive feedback. You see that to make the circuit stable, I do not need this positive. This we have discussed when we have discussed in general the enhanced negative feedback topology. This is called the negative feedback with positive feedback, or there is another name we call it enhanced negative feedback topology. Here you see that we are giving some certain amount of positive feedback, some great advantage you will get if you give certain amount of positive feedback in a negative feedback topology, that will be discussed now. You see from the circuits I can write that V naught S by V in S minus S R1 C1 minus 1 minus 1 upon K S square plus N S 1 upon R2 C1 plus 1 upon R2 C2 minus 1 upon K minus 1 minus 1 upon R1 C2 plus 1 upon R1 R2 C1 C2. Here K equal to 1 plus RB RA, these two resistances are different. I want to distinguish it from the positive feedback topology. That is the reasons we have given the name RB and RA, right. Now, pole frequency and pole selectivity of the and gain constants will be given by omega p equal to 1 upon R1 R2 C1 C2, QP equal to 1 upon R1 R2 C1 C2 and upon 1 upon R2 C1 plus 1 by R2 C2 minus 1 upon K minus 1 upon R2 C2, right. You see that we will get some advantage if I get, you see look here these functions, this is a functions, this is a function, is that there is a subtractive term at the denominator. Now, why it is, let us look at sorry. If I can go back, so it is actually if I now why I am telling you, see here what will happen here. Let us take a blank page, it will be more clear. You see in the enhanced negative feedback topology what we got it, we got a subtractive term, is not it. QP is a, I can write like this one, x1 x2 minus x3, is not it. This is in the enhanced negative feedback topology. Right. Now, you see that in all the previous cases we will find, in all the cases, that means if I whatever the we have so far discussed, that means the single amplifier, we have discussed the positive feedback topology, okay. That means we have discussed the silent key circuit, is not it, low pass, high pass, band pass, is not it. In all the cases you will find, that QP or the pole selectivity is given by some x1 by x2. Now, what is this x1 x2? Actually, this x1 x2 actually you will find there is a ratio of some capacitance or capacitance or resistance, is not it. So, in all the cases you will find if I want to make this high, this I mean if I want to make this pole selectivity high, my this ratio is to be high. This ratio is only high, you will find, if I use a large element spread to make, that means all the single amplifier structure, that means in positive feedback and as well as in the simple negative feedback topology, that means silently all the cases, that means low pass, high pass, band pass, as well as the multiple feedback negative on the multiple feedback circuits or the negative feedback circuits without any positive feedback, you will find that the QP is directly proportional to the element spread. I have to make element spread very high to make the QP high. This is very undesirable. That means I have used large capacitance ratios. That means if the one capacitor is 1 picofarad, other capacitor might be several thousand picofarad, which is not acceptable. Or if one resistance is 1 kilo ohm, if the QP is high, the other resistance might be some mega ohm. So that is not desirable, right? Whereas you will find that in the enhanced negative feedback topology, that means the negative feedback topology where you give certain amount of positive feedback, my expression of sensitivity or selectivity, I am sorry, is coming like x1 upon x2 minus x3. Look at this subtractive term, this is very important, right? I should take some other, look at this subtractive term. If I make this difference very, very small, my QP will be very, very high. If I make x2, that means x2 almost equal to x3, however, x2 not equal to x3 and x2 greater than x3, then what will happen? I will get large pole selectivity. Okay. So, in the case of band pass filters, this large pole selectivity is great advantage. So, that is the reason we talk about this band pass filters with the, because the circuits which I have discussed is basically band pass filters with a negative feedback band pass, negative feedback circuit band pass filter or RC networks in the negative feedback path, and we have given some positive feedback to it. Let us go back to the actually. So, this is our 59, I think. Yeah, this is 59. I am sorry. Yes, this you see. Yes. You see, this is the basic band pass circuits we have discussed. These band pass circuits we have discussed, is not it? So, this is an enhanced negative feedback band pass circuit. That means negative feedback circuits with positive feedback. So, in band pass circuits, always it is desirable that the selectivity should be higher and higher. That is a good. Why? Quite obvious if I see there here. So, that means what will happen if I say why I am telling, that means if the frequency plot if I make omega and gain here, larger the Q, more and more will be the selective networks, okay, is not it. So, the Q increases, right. So, Q increases here, is not it? Now, what is Q? You see the Q in the terms of frequency. So, what will be the Q? Q will be like this one. So, we will take this frequency, suppose this is omega naught minus 3 dB point, okay. I mean from coming from this minus 3 dB. So, I will take this one, okay. So, it will be, suppose this is omega 1, this is omega 2. So, the Q will be omega naught upon omega 2 minus omega 1. Can I take color different? That means Q equal to omega naught upon omega 2 minus omega 1 or omega naught by delta omega or f naught by delta f. So, the larger and larger the Q, higher and higher you find the delta f will be smaller and smaller. That is our requirement, but how will I achieve that in actual circuits? I can achieve only if I have a structure like that, right. If I have a structure like that, you see here, you see this term minus 1 upon k minus 1 by R1 C2. Let us look at the expressions of Q. You see this is the subtractive term. So, obviously, these I can write this I can write like this one. So, this is let me take I can write so I can write this one as x1, hold this as x2 and hold this as x3. So, x1 I can write upon x2 minus x3, is not it. So, I can do it by controlling the k. You see, I can make x2 very nearly equal to x3 by controlling k only, because these elements already determined R1, R2, C1, C2 already determined by this omega p. So, by controlling k I can make this. So, I can make the selectivity very, very high. So, that is a great advantage of the single amplifier enhanced negative feedback topology, right. So, capital K, which is gain constant upon 1 minus R1 C2 minus 1 minus 1 by K. Now, disadvantage, what is the disadvantage of the single amplifier structure? One of the problem of the single amplifier structure, you will find the sensitivities are rather high. If you compare with the state variable structures and all this, sensitivities will be high. Also, the tunings is very difficult in this type of filters. What is tuning? Let us go back, will be more clear. You see that once you design the circuits, you will find that I am designing circuits with or synthesizing the circuit with some I have some intention to get a particular value of omega p, right. With R1, R2, C1, C2 everything will be there, right. But the problem will arise, you will find that I may need little bit of tuning the circuits after fabrications, whether you are doing in discrete circuits or you are doing in some integrated circuits, some little bit of tuning is necessary. Suppose if it is omega p is prescribed is 1 kilohertz, I got 900 hertz. So, I need some tuning. That means, I have to choose some value of the resistance which I have to vary to get the desired value of omega p. The problem in this type of single amplifier structures we will find that you see this, if I tune, if I to get, suppose after fabrications I got 900 hertz, to now to get its 1000 hertz, the problem will be, or 1 kilohertz, the problem will be if I tune, the QP also will change, because this R1 is common in both. So, there is no element you will find which is there in omega p, but not in QP, or which is in QP, but not in omega p. So, the orthogonal tuning similarly for K also, if you assume that I have to tune, or I have to tune all the 5 parameters omega p, QP, omega z, qz, okay, and K, it is just impossible to make the orthogonal tuning by the single amplifier structure. That is a great drawback. Now, I talked about the sensitivity, but sensitivity is looked like you see here. Now, logarithmic sensitivity we should define like this. Logarithmic sensitivities is given by, you see that in many cases we have found that omega p equal to 1 upon root over R1, R2, C1, C2, is not it. Now, logarithmic sensitivity is something like this, that means sensitivity of omega p with respect to R1, R2, C1, C2, or I can write in generalized form that sensitivity, suppose I am sorry, that means S y, y is a parameter, filter parameters, with respect to the passive elements x, I want to find the sensitivity will be okay, delta y by delta x by x, or I can write del y by del x by x. Okay. Best thing to find the sensitivities, that suppose if I have the expressions like this one, omega p equal to 1 upon root over r1 r2 c1 c2, you take the logarithm of both sides. Okay. Natural log omega p equal to minus of half natural log r1 r2 c1 c2. So, this will be minus half, obviously natural log r1 plus natural log r2 plus natural log c1 plus natural log c2. Since it is partial derivative, what will happen, you see that you will, once you vary r1, all other things will come. Now, if you take the derivative of this, then what will happen? I will get on the left hand side, you see, if I do it here, I will get on the left hand side, if I take the derivative, okay, delta omega p by omega p equal to minus half, suppose if I take delta r1 only, I am varying the delta r1, so r1 sorry, so it will be by r1, right. So, the what is the sensitivity now? If I write, that means S omega p r1 will be delta omega p by omega p, delta r1 by r1, in this case it is minus half, right. And interestingly, you see that in this case, that since omega p is equal to root over 1 upon r1 r2 c1 c2. So, S omega p r1 is equal to minus half, I can write S omega p r2 S omega p c1 S omega p c2, or in combined way we can write like this, that S omega p r1 r2 c1 c2 equal to minus half, right. So, this is sensitivity. So, similarly I can find the sensitivities of QP, right. So, typically what we will find, I mean if you have the all the elements, suppose in your transfer functions, most of the transfer functions which you have written, that it is the parameters, filter parameters we are more interested are omega p, sorry, let me take a new page, omega p, QP, capital K, okay, and if possible omega z and QZ. Clear? So, these sensitivities you have to find with respect to the passive elements. If that particular passive elements are not in the expressions of omega p, so with respect to that, so obviously sensitivities will be 0. What is that? You see, look at, if the omega p, my expression is 1 upon root over r1 r2 c1 c2, right. So, if I may ask you, what is the sensitivity with omega p with respect to small r1? That is also there in the case of positive feedback topology. Since it is not there, so it will be, because if I vary small r1, how much our pole selective pole frequency will change? Nothing, is not it, right. So, it is obviously 0 because it is not equal to, obviously again S omega p small r2. Clear? This is our sensitivities figure, right. So, this way obviously I can find also the sensitivity with respect to QP, that means QP with respect to all the elements R1, R2, let me take new page. So, it is QP with respect to R1, R2, C1, C2, small r1, small r2 in the case of positive feedback topology. Also Sk gain constant r1, r2, C1, C2, small r1, small r2. This may not be same, SQP r1 may not be same with the SQP r2. In the case of pole frequency, it is same because all are in the denominators under the square roots are becoming same, but this may not be the same, right. Once I talk about that, you see in the case of your univariate amplifier design, some of the sensitivities are 0, you will find exactly that some of the sensitivities, especially the QP sensitivities, you will find SQP sensitivities for the unity gain amplifier design is 0 for some of the elements, okay, not for all the elements, right. So, this way you will find the sensitivities. So, the problem with the single amplifier structure, as we have discussed, is basically you will find that disadvantage of the single amplifier, that sensitivities are extremely high. Number 2, component spread is also high, right. Most of the cases you will find, except if you take, because if you do not say the sensitivities are okay, I say that I will take some other structures where the sensitivities are not high. Suppose if I say surrogate design or if I take unity gain amplifier design, right. In that case, we will find that the sensitivities are 0, but the element spreads are very, very high, which is also not acceptable if you want to make your filters in a very in integrated circuits, right. So, component spread is also high. So, that is not also acceptable. That is a problem with the single amplifier structure. And quite obviously, you say that I will make QPs less, but QP is not in your hands. I mean, somebody asks you, suppose in some signal conditioning circuits, I need a very large QP. So, in that case, your component spread also will be very high if you use even unity gain amplifier structure, right. And orthogonal tuning that I discussed, this is also not possible. Okay. Orthogonal tuning is just impossible in the case of single amplifier structure. So, these are the typical drawback of this single amplifier structure, but obviously, you see that if I can suppose sensitivities we are talking about, suppose tomorrow some technology is available where I can make our desired value of the resistance and capacitance precisely. Okay. So, it does not matter if the sensitivity parameters are high, because I have exactly designed the resistance value and capacitance value. So, in that case, even though sensitivities are high, I will get the desired value of the desired value of the filter parameters omega p q p, okay, omega z q z and capital K, right. So, it is very cheap, it is very small, noise is also, because if you increase the number of amplifiers, your noise problem will also will be predominant. So, these are the typical problems in the higher amplifier structures. However, we will see that we will in a subsequent lessons that we will go for 3 amplifier structures where we can achieve this orthogonal tuning. Also, the sensitivity figures will be less. Okay. With this, I come to the end of the lesson 22. Thank you.